Welcome to Math 31. This is a lesson on the slope of the tangent line. Interesting lesson in that it is very similar to a lesson we looked at a while back, but now we're going to develop a better method to calculate or to determine the slope of a tangent line. In fact, better than that, we're going to come up with a formula that we can use to calculate the slope of the tangent line at any point on the curve. So this is a more efficient way to do things. In fact, as well, this is a very important bridging unit because it's going to lead us into the next unit, the derivative. So what we're doing today is extremely significant down the road. So just to refresh our memory, if we looked at any function such as this is a quadratic, and we note point P, any point P really, but if you want to find the slope of the tangent line at point P, the general method that we have been working with is we pick another point Q. And we're aware that point P, the coordinates are going to be x, comma, f at x. Then the points of Q would be, if we remember that the horizontal distance between P and Q is h, point Q is going to be x coordinate x plus h, and then the y coordinate f at x plus h. So we pick that point. And then let's take a look at this again. If you're trying to get the slope of the tangent line based on that, we use the slope formula. And of course the slope formula is m is equal to y2 minus y1 divided by x2 minus x1. So using limits, and this is the big step forward we make. Like what we did previously was we would, for a specific point on the curve, we would make that h very small. And that would allow us to solve for the slope. But here, using limits, as the horizontal distance is as small as possible, so as h approaches 0, we can get this sort of formula. Subtract the y coordinates, so f at x plus h minus f at x, and then the x coordinates, x plus h minus x, would be your denominator, which is always going to leave you with h. So we make that h value as small as possible. Take the limit. Now remember, when you're taking the limit, you're finding out as the x, or in this case the h, gets smaller and smaller, what is the corresponding value of the expression. And then that is going to give us a formula that we can use for any function to get the slope at this general point x comma f at x. So this is a very important one, and make a little mental note of this. And this, by the way, is called, for your information, this is a preview of what's coming up in the next unit. This is called the derivative of f at x. And you'll be seeing this notation very soon. But one of the ways we write the derivative is f prime at x, and it means the formula that is used to calculate the slope of the tangent line at any point on that function. All of this is defined in detail in the next lesson, but for your information. So let's do a question like this. Determine the slope of the tangent line of f at x is equal to 3x squared minus 6x plus 4 at any point x comma f at x. Now the graph is right there, and we're not locating it at any specific point, so we could be getting the tangent line there at the very vertex. Now you might note by inspection that m is equal to 0. That one has significance down the road as well. But you could also be finding it right there that's tangent at that point. The slope of the tangent line is always changing. And then finally this one. Actually, I said finally, but there's an infinite number of points on the curve. So the slope is always changing, but one formula will work for all of them. So I'm just going to back this up a bit. Let's do that. Now, important to use this formula that we got. m is equal to the limit as h approaches 0 for f at x plus h minus f at x divided by h. So make that note. You'll be using this one a lot. And your 2 points, I'm just going to also put this above. F at x is equal to 3x squared, or not your 2 points, but your function, 3x squared minus 6x plus 4. Then f at x plus h is equal to 3. So everywhere you see an h, replace it with x plus h, minus 6 bracket x plus h plus 4. It would mean that these can be plugged into the formula. So m is equal to the limit as h approaches 0 of 3 times x plus h squared minus 6 times x plus h plus 4. Big old bracket around it, minus f at x, which is 3x squared, minus 6x plus 4, close bracket. All this over top of h. So you have to be very careful. Clean this up with caution. It's really just a polynomial problem, but historically, when mistakes are made, they seem to be made right here. So I'm going to work out that numerator with care. I'll do this in a couple of steps, but x plus h squared is x squared plus 2hx plus h squared, all that multiplied by 3, so keep that bracket up, minus 6 bracket x plus h plus 4, and then minus that polynomial gain, 3x squared minus 6x plus 4. And then all over top of h. Now I can still fill this in below. I'll get at least one more step done. The limit as h approaches 0. So now that 3 gets distributed in, so we get 3x squared plus 6hx plus 3h squared. Distribute the 6 in, minus 6x minus 6h, that's an h, not a 4, it looks, plus 4. And I'm also going to remove the second bracket, so I'll distribute the negative in there. So minus 3x squared plus 6x minus 4, all over top of h. And here's where we get the payoff. There'll be a lot of cancellations. The plus 4 and the minus 4 go away. The 3x squared and the minus 3x squared disappear. Minus 6x plus 6x also gone. So when we're all said and done, we get m is equal to the limit, or basically said and done, as h approaches 0. All we have left is 3h squared plus 6hx minus 6h all over h. And I will get a clear screen to write on in just a few seconds. And you're probably thinking, as am I, that this is not that unfamiliar of a situation now. We can factor out an h from the numerator and then simplify. Now you're probably thinking as well, why not factor out a 3h? You're entitled to. I'm not going to bother because I look at the denominator and I can see that it's not going to cancel anything out, so I won't bother. So this now, excuse me, so m is equal to the limit as h approaches 0, and we have, I believe, 3h squared plus 6hx minus 6h, or 6x, all, my memory is going bad, minus 6h, sorry about that. all over h. So we factor out the h. That will leave us with 3h plus 6x minus 6 all over top of h, and this is the limit. Then we divide out the h's. So the slope is equal to the limit as h approaches 0 of 3h plus 6x minus 6. Now we take the limit. So the h can be replaced with 0, and we'll get 6x minus 6. So that is the slope. And the symbol we looked at earlier was calling this f prime at x. And this process, for your information, is called taking or finding the derivative more technically, or differentiation. So that's a word you're going to be seeing a lot very soon, by first principles. Now, taking the derivative or finding the derivative or differentiation is probably the most important thing that you do this term, at least in this course. You don't get much easier than this. This question in the future, like in a few days, you'll do the same, get the same answer in about 2 seconds. So this is a long, lengthy method. That's first principles. We do get speedier at it. Don't worry too much about the notation yet. That is all getting taken care of in the next few days, but that's for your information. So this 6x minus 6, which we call the derivative, is a formula that we use to determine the slope at any point along the way. So this is a formula to find the slope of the tangent line to y equal f at x at any point. Now let's finish this question off, and then that's going to be the end of this lesson. The next lesson we'll go through a few more examples, slightly more complex ones. So this question, same formula, same function, but we want to get it at x is equal to 3. So specifically at that one point, right there. So what we do, going back to the previous question, we note that f prime at x is equal to 6x minus 6, which is the slope. This is a formula that we use, I'll just write that m equal, to find the slope at any point. So because we want to find it at x equal 3, we just work out f prime at 3. So we substitute in the 3, and then we get 6x minus, or 6 times 3, minus 6, and f prime at 3 is equal to 18 minus 6 is 12. So therefore, the slope of the tangent line is 12 at x is equal to 3. And you can tell by inspection it is quite steep. So that does seem reasonable. And had you wanted to work it out at x equal 1, the slope should be 0. And in fact, it would be if you did plug it in. 6 times 1 minus 6 does give you 0. So this formula is reliable. It allows us to calculate the slope of the tangent line at any point. Extremely important, because this really is one of the two big things in calculus. And finding the slope of tangent lines to curves makes applications, all sorts of applications possible. If you think back to physics, where you're dealing with velocity and time and distance, and how important the slope is in those cases, we now no longer need straight lines, linear graphs, in order to calculate the slope. So any sort of rate question, speed, acceleration, now we can handle more complex graphs, which is one of the things that we do in the next while. So that's the end of this particular lesson. The next one, as I said, we'll go through some more examples of that. This is sort of a sampler of it. Thank you for your time.